Okay, we'll go ahead and start. So I guess congratulations for surviving the midterm. I suppose that was last week, but still, I should probably say that. Oh, I was also going to let people know that, like for example, on things like the midterm and other times too, we are not proud and we steal student solutions, just to let you know, right? So we go into it. I think there was one where we asked for some DCP representation of like what inverse product or something. We'd figured out 2 or 3 of them. And actually amongst you found several others. And we just happily put them into the solutions, just so you know. So sometimes we give a heads up, like you'll see that if you look at a homework solution, because the homework problem started life as maybe a final exam problem. And sometimes we'll say, here's our solution. And you say, here's a far better solution submitted by a student. So we'll sometimes say that. But I just want to make it public that we steal your solutions if they're better than ours, happily. What's that? Do we get paid? No, not really. No, it's an honor, right? If you look at the solutions and you go like, whoa, that's my solution. And just think of it, right? Students, generations of other students will read their homework solution and look down there and they're like, whoa, that's like, who would have thought of that?
Will it have my name on it?
Ah, yeah. No, we don't attribute. Yeah, we don't. We theoretically we know, right? Because it's somewhere in some email. It's like errata for the book, right? Oh, by the way, and actually people in the class have found several things that were just like wrong. So, I mean, the main points are still valid, but I think we're at 2 and growing. So that's pretty good too, because people have been looking at it pretty carefully for a long time. So, and they're just, so anyway, so thanks to those people as well. So, okay. Let's see. Were there any other announcements? That was it. Good. Let's see. Any questions about midterm, finals, where we are, what we're doing, all that kind of stuff? Okay, that's a no. So okay, good. We'll continue. We'll continue. Last time we'd looked at this binary hypothesis testing, right? Which is, I mean, in some ways, it's the essence of kind of like all of statistics, right? It's you have in this case you have just 2 distributions. You observe one sample, and the question is, which distribution generated it, one or the other. And if you make that more complicated and have distributions not on a finite number of points, but on Rn or something like that, or more complicated things, and you have more than 2 hypotheses, then that's kind of most of statistics right there. But anyway, so this is a very simple setting, and so the question was to make a guess about whether an observation, right? And an observation is like a number like 3. That's an observation, right? That's what happened. And then your goal is to try to figure out, did it come, or guess in some intelligent way, did it come from this distribution or this one, right? And we looked at that. You end up with, you have this idea of a randomized detector. It's a policy that says when you observe this outcome, which distribution do you attribute it to, right? And that you do with a 2 by n matrix, where the columns give you the probabilities that you announce it came from, P or Q, the 2 different distributions, right? So that's how that works. If those are all 0s and 1s, then it's deterministic. And you write this down as a bi-criterion optimization problem. There's 2 things you care about, the probability of a false positive, and that's PFP, and the probability of a false negative, right? And these are you just get these from matrix multiplication. And the point is that each of these is a linear function in T. T is what describes your detector, right? Anyway, so this problem, it turns out, is actually really quite straightforward to solve if you scalarize it. So you say that lambda now is the amount, is the factor that relates how much I care about, false positives versus false negatives or something like that. Then it turns out it just has a super simple solution that looks like this. Lambda is that weighting factor. For example, if it's 1, it says actually, I just want to minimize the number of errors, period. That would be lambda equals 1. And then the solution is like analytic and it's been known since, I don't know, probably 1900 or something. And it basically says, in that case, and it's completely reasonable. It says if lambda is 1 and you want to minimize, say, the total number of errors, you would say, well, what I would do is if I will choose the distribution which had higher likelihood. And we'll see that in other contexts, or we've already seen it in the context of maximum likelihood, so that's an example of that. And the lambda allows you to put weights on the two different types of errors, which I think are called type 1 and type 2 error, but I can never remember which is which and just look it up every time I need to know. Actually, usually I try to avoid situations where people are saying things like type 1 and type 2 error. So I usually walk out of the room, but if I am forced to, I will just look it up to figure out what it is. Okay. Now, what's interesting is even at this like super simple problem, you can get into weird things, very interesting stuff like this. Suppose you say, I want to minimize the maximum of my false probability and my false positive and false negative errors, right? That will get you something that's Pareto optimal because max is a monotone function of the two. It's a monotone mapping from the two criteria into a one. So that is a scalarization. It's not a linear scalarization, which is what's normally employed, but it's a scalarization, right? And that turns out that's an LP, and the solution is usually not deterministic, right? So here's an example. So here we go. Let's see. Here's the trade-off curve of false positive versus false negative. That's this thing, this curve here. And oh yeah, somebody explain the point at the top. First of all, let's talk about what's really good about that detector. What's the probability? If we use the detector up there at 1, this point right here, this one. First, let's say the good part about it. What's the good? What is the probability of a false positive for that detector? 0. Right. Okay. Fine. Right. By the way, what does that detector do? It just returns like negative every time, right? So it's kind of silly. But the good news is it does have a very, very low false positive rate. Okay. So and that's anyway. Each of these correspond. These correspond to likelihood ratios between the entries there. Right. It's what is your if, in fact, you can even take lambda and put lambda around here and ask what happens if you have a certain lambda like that. The optimal point you're going to find is going to be like here or here or here, right? The minimax one is one you can figure out what that is. This is the x equals y line, and the minimax one you find by simply taking this rectangle or square, if this was done correctly with axes, which it was not. And you simply grow it until it touches this curve. And that's going to be right here. And so it turns out if you wanted to minimize the maximum of your false positive and your false negative, you would number one, you'd have a non-deterministic detector, which is weird because you'd say, oh, the outcome was, I don't know, let's say 2. And you'd go, oh yeah, okay, well then that's definitely like P, right? And then you'd come back later and say the outcome was 2, and you'd say, I don't know, let me check just a minute. Oh, it's Q. Everybody got this? So it's a little bit odd that you would have a randomized detector, but this comes up in a bunch of things. By the way, a randomized detector you can think of as a relaxation of the original. The original sensible problem is to say, no, if there's an outcome, you have to commit to one of these two distributions. You can't do something weird and have an inconsistent, weird probabilistic thing. That's right. So, okay. So, all right. So that's very baby example. Okay. Last topic in this section is going to be experiment design. This is actually super interesting, also like super useful. So the setting is we have a bunch of linear measurements here. So we have linear measurements. And AI you can think of as the measurement vector. WI, we're going to normalize those to have all the same standard deviation, which is 1, right? And so what it means, roughly speaking, the size of A is something like, and this is dialect, but signal to noise ratio, okay? So, right, because if A is gigantic, right, then it says that the AI transpose X tells you a lot, and then I add this noise that's like plus minus 1, like who cares, right? If AI is small, it means that's a pretty crappy measurement. So that's the idea there. Now, if I get a bunch of these measurements, these yi's, and I ask someone to guess x, and the maximum likelihood, which is just nothing but least squares, the estimate is just least squares. So you just get this, right? It's the sum of AI transpose, that's this thing, inverse times this, right? And the error, which is x hat minus x, has zero mean, so that's an unbiased estimate. And it has a covariance, which is given by this matrix here, okay? And if you wanted to work out a confidence ellipsoid for that, again, assuming, because these are all Gaussian, this is Gaussian, it would look like this. It would say it's a set of x which are centered at your estimate x hat, and the shape is given by this matrix here. And so, for example, I don't know. So that would give you, and beta is going to be determined by actually it would be something like the inverse distribution of a chi-squared random variable with the appropriate number of degrees. It doesn't matter though, because that's how you would get beta, and that would say thank you for the measurements. This tells you, with 90% probability you're in this ellipsoid, right? And if I say 99% thing, then beta just gets bigger here. So that's all that happens, right? Okay. So experiment design is this problem. So I have a bunch of candidates, V1 through VP. You should think of these as possible measurements or experiments you can make, right? So that's what they are. And then I want to choose M AIs, which are among this palette of possible experiments I can carry out, right? So in other words, I have a bunch of sensors, and what I can do is you'd say, pick which sensors you should use. In fact, even pick the sequence, right? Which you should use to actually get the best estimate. The best estimate is a bit tricky because we're going to measure everything in terms of this ellipsoid, right? And we want this positive definite matrix, right? And what we really want is this positive definite matrix to be small, which by the way is the same as saying that we want this to be small, which is saying that the confidence ellipsoid is small, right? So that's what you do. So in other words, now the problem with that is, this is exactly an ordering, the positive semi-definite matrices, which is not linear, right? So it's completely reasonable if you came up with an experiment design and you came up with one. We looked at your E's, like E1 and E2, and they were not comparable. So in some directions, you're better, and in other directions, you're better. That can and does happen. Everybody got it? So we're going to have to scalarize that the idea of a positive definite matrix being small, and there's lots of different ways to do it. And each one is going to lead to a certain named type of experiment design. So let me discuss a couple of things quickly. Earlier, I said that the size of A is something like let's say the 2 norm. That's something like a signal to noise ratio, right? If AI is gigantic, that's really good. That's a good measurement, right? So let me ask a question. Here, in fact, I have a proposal. Here's my experiment design method. Ready? I will find the largest VI in magnitude. Someone says, why are you choosing that? And you go, of the sensors or the experiments I've been offered, that's the one with the highest signal to noise ratio. Make sense? Okay. And then they'd say, ready for my experiment design? Just do that. Suppose V7 is the largest in magnitude of these, then you just do that the whole way, all the way. And someone says, why are you doing that? And you go, why would I use anything other than the experiment that has the highest signal to noise ratio? Everybody got that? Okay. Okay. You're probably not going to fool for it, but I'm actually pretty good at making up I could tell stories around that and all sorts of other stuff. I bet I could get some people to go for that. Okay. Any comments?
You want the worst situation, not the best situation. For single ones.
Well, I mean, no, I just told you my policy. My policy is I'm going to take V7 over here because it's the one with the largest magnitude, right? And then I'm just going to, all my AIs are going to be that. You have a suggestion? Any comment on it?
Would there be some bias in one direction?
No, you know, all of these are kind of unbiased. Yeah. Let me ask one question. Let's talk about this matrix if all the AIs were the same. What's that matrix look like? What is it?
A7 square identity.
It's what?
The whatever parameter A7 and there's a A7 square and an identity matrix.
I don't see any identity matrix. What's that? No.
Matrix.
Yeah, so this thing would become sum from I equals 1 to m V7 transpose, otherwise known as m times V7 transpose. Anybody ought to comment about the matrix V7 transpose? It's what? It's rank 1, right? Okay, so if I just always use the experiment with if I always make a measurement which is the highest signal to noise ratio, then we got a kind of a problem here because this matrix is not invertible. It's singular, right? And so, I mean, we could talk about E inverse if you like. It's kind of silly. I can tell you what it would be. It's our error covariance. It'd be really good in the direction V7 because I blew every experiment I ever did was the same experiment, right? But in n minus 1 dimensions, in n minus 1 dimensions, I got no information of any kind whatsoever. And so my confidence ellipsoid is like infinite in those directions. Everybody make sense? Yep. Okay. So that's it. Okay. All right. So, the first thing there's another thing we can observe here, right? Here, we don't have to choose the sequence, right? Because the outcome doesn't depend on the sequencing, right? So, in other words, there's no difference if someone says, please do the following. Use V1 4 times, then V3. And then here's the trick. Switch back to V1 4 more times, and then V4. Everybody got what I just said? Okay. So it turns out, doesn't matter. If you look at our objective function here, it's symmetric. You can permute them any way you like, right? By the way, this is completely false, except in this incredibly simple Gaussian setup, right? In other cases, you want to do design of experiments. It's a whole sequence, and it depends on what you've observed so far. Right? In other words, the best, if we're flying a drone and someone says, we have an energy budget, which sensor are we going to use, right? It depends on all sorts of stuff. But in this Gaussian model, actually, it doesn't. So, okay. So it really only depends. I only have to tell you how many of my total budget is m experiments. I just have to divide m up across the palette of potential experiments that I've been offered. Okay? So if I had 22, I could say I want to do 4 of these, 7 of those, 3 of these, and blah, blah, blah. And my numbers better add up to 22. That's all we have to do. Okay. So we'll write it this way. And here we have an integer problem, right? Because the m's are integers. Actually, here mk is the number of times I'm gonna use experiment k or sensor k, right? That's what it is. And then this thing just looks like this, right? Okay, so this is all cool. Let's see. This is actually, if m were not an integer but a real number, positive real number, this thing would actually be k convex, where k is the PSD cone, right? So this would be cool, right? But it's not. M is an integer. Okay, and now. By the way, this comes up in lots and lots of settings where there's an integer or something like that. And then, so you do, I mean, it's kind of one of the themes is you do relaxation, right? So the relaxation is, you know what? I divide the m's by capital M. So instead of working with M1, I'm going to work with M1 divided by capital M. And then you're saying, what is the fraction of the total number of experiments you're going to do that are going to use, in fact, M1 over M what is the fraction when you use experiment number 1? Everybody make sense? Okay, so now if I do that, we still have the constraint that those fractions are integer multiples of 1 over M. Okay, so now what we're going to do is we're going to relax it, right? So we're going to simply ignore that last constraint. That's a typical relaxation, right? Relaxation in general just means You made the feasible set bigger, right? That's all it means, right? And so we do that. Okay, now this is actually, it's kind of cool if, so we're going to relax it like this. And then there's all sorts of things you can do with this. So we'll talk about solving it. But what's going to come up is you say, actually what I'm really going to do is I'm going to choose for you the fractions of each of the experiment types that you should use, whatever your budget is, right? Maybe it's not going to fit into the integers, but if m is big, I don't think this is a problem, right? And then I'll give you lots of hints about what you could do. What you can do, first you go back to the person who said do the experiment design, and you'd say, yeah, okay, what's your budget? And they'd say 57, and they go, great. You should use experiment number 2 6.45 times. And they would go like, what does that mean? Like, that means nothing. I can't use every time I'm allowed to choose one of the experiments, and I can't do it 6.45 times. Everybody see that? Okay, at this point, and this is just like very practical advice for all of you as when you become part of the 364A diaspora, here's what you're going to do. The first thing you do is you try to convince the person that your relaxation is actually much more sophisticated. And you'd say, oh, yeah, no, look, don't tell me about 6 or 7. I don't care about that. This is much more sophisticated. You can drop things like, you can make reference to quantum mechanics. That sometimes helps, right? Because you'd say like, look, it's not like you just choose an experiment each time. Anyway, you could say this is really like a probability. These are, in fact, the lambdas are going to be probabilities. And then it says, here's what you should do. Every time you should roll the dice with probability lambda. And if 13 comes up, congratulations, you should do experiment 13. Everybody following what I'm saying? Anyway, some people actually fall for this. It's actually kind of amazing, right? And you mentioned that, and you mumble about quantum mechanics and things like that. It's much more sophisticated. It's a probabilistic thing. And you can hint at other things like, hey, do you remember like matrix games? Do you remember how there's like generally not an equilibrium, and so you have to have a what's it called, a randomized policy? And they would go, yeah. And you go, well, it's just like that, right? Anyway, that's fine. But supposing, in fact, you really had to do, someone said, no, dude, the drone is flying and you have a budget of 120 experiments. So I need integers, right? So someone tell me, what would you do? What would you do?
Threshold big.
Threshold, yeah. I mean, do you mean rounding? Yeah. Here's what you do. You'd find your lambdas. It's going to be sort of it's a continuous, probability that you choose the experiment at a fraction, right? And you just round them, right? By the way, if you round them and then you add up the rounded things and they come up to 121, what do you do then? Just reduce 1. Okay, that's what you do. Everybody following this? And I'm not kidding with this. And you say, that's my experiment design. And they would say, awesome. And they would say, is that actually the one that is going to minimize is that going to give me is that going to be the best one? Is it going to minimize this confidence ellipsoid? What's the honest answer to that? No. Yeah, okay, probably would work. That's fair. That's one way to say no. But yeah, so you'd say, does it solve they'd say, does it actually solve this problem? And you'd say, I don't really know. But what can you do to give some evidence that your rounded one is not so bad?
Could we do the dual problem?
Yeah, you don't even need the dual because this was a relaxation. So what you do is, we'll wait until this will make more sense when we scalarize this, right? So let's say, for example, what happens is you end up with the volume of the confidence ellipsoid. And someone says, does that choice actually minimize the volume of the confidence ellipsoid? And you go, actually your answer was perfect. Probably. You'd say, it's very close. And they'd say, well, how do you know that? You go, well, because when I remove the constraint that these things are integers and I solved this problem, I found that the log of the volume was 12.6. And you'd say, nobody could do better than that. That's if we ignore this silly constraint that these things are integers. And you'd say, my log volume was 12.7 when I rounded. Everybody got that? Then it's done, right? Then you're just done. Because you just say, I can show nobody can have a volume Did I get that right? I did get it right. No one can have a volume less than 12.6. That's something you can, but we got one that has log volume 12.7. Okay, make sense? Okay. All right, so this is relaxed experiment design. Actually, we will get to the dual of this very soon. Yes?
Why is it the assumption of M must be much greater than the number of experiments?
Sorry, where? Here?
M much greater than P. The assume
Why is
in the relaxed experiment design, assume M much greater than P, and then using lambda k is equal to mk by s.
you mean over here?
Yeah. Why is that there?
Let's see why. Oh, the idea is I wanted these numbers to be reasonably to be not too grainy. I want, if I round it, I want to be able to get something that's close to an integer. I mean, you don't even need this, right? The first one, that doesn't matter, right? Yeah. Now, when you get down to a, well, okay, let's try this. What if I said you have 3 experiments? Period. Can we solve that problem? I mean, it depends how big whatever it is, P is, right? P is the number of options, right? Well, let's suppose P is 20 or something. And I tell you, no, you have 3 experiments. Tell me what to do. Can we solve that?
Just try all the combinations.
Yeah, you try all. It's like P cubed. You try all combinations or whatever. It's not even P cubed. It's a lot less than that. It's right. P cubed over 6, right? Or something like that, right? You try all of them and you find out. Okay, so for small ones, we can actually solve the actual, and that's actually when you get into things like design of experiments, these are like grainy and, they're kind of combinatorial, right? And these are tricky. Yeah.
So perhaps I didn't understand what you meant before about like E not being invertible, but doesn't this not require that E is invertible? Because you can make a solution where M1 is equal to M.
Yeah. So you're going to have a problem though. Let me show you what the problem is. That when this is not invertible, we're going to interpret E as being basically infinite in those directions. And we've asked you to minimize it. Now, by the way, when we scalarize it, we're going to be cool, right? Because we're going to have a log, a determinant, or a trace, and all that kind of stuff. And the problem is then you'd say, if you do that, you're going to come up with plus infinity. Yeah, and we'll get to that in a minute. Yeah, but that's...
It's the fact that your objective function, or your objective function is making it undesirable for it to be.
Yes, in fact, in this case, infinitely undesirable. Yeah. So what we'll do is we'll say that if this thing is invertible, we'll say then E is infinitely undesirable. By the way, when we scalarize, that's going to happen automatically in a minute. Okay? So, okay. Okay, so now you have different names, right? And these are like famous names. So D optimal, duh, is going to be the determinant, right? So if you minimize the log determinant, and that's actually beautiful. Basically, it says minimize the volume of a confidence ellipsoid at some level, right? Because that's what it means, right? And by the way, here, your question, we can be very specific. If I choose, let's say, lambda equals E1, that means I'm simply only going to do experiment 1. Then this matrix is, not invertible. I could take the -1 and put it out here, but then log determinant of a non-singular matrix is going to be minus infinity. Of a singular matrix, it's going to be minus infinity. And when I flip the sign, I get plus infinity. And it's like, nice choice of experiment design, but your objective is infinity. And given that we're minimizing it, I would call that a rather poor design, right? So I don't know if that explained that, but okay. All right. So this is called D-optimal experiment. There's whole books on this, which is kind of cool, I think, but that's okay. All right. You can actually work out the dual problem of this, which is actually a dual, right? And it turns out to be something that we're going to talk about possibly even later today, but it looks like this. You're going to end up with a maximize of the log determinant of W. W is going to be like a dual variable, plus a constant. And then you're going to have subject to this constant here. And this thing, let's just check that is in fact a convex optimization problem with variable capital W, right? This is concave. Log determinant of a positive definite matrix is concave. That's a constant, doesn't make any difference. What kind of inequality is this as a function of W? What is it? It's linear. It's just linear inequalities on W. It's quadratic in V's, but the V's are given to us. Those are the options for experiments that we carry out, right? So, okay. And we can actually interpret it really well. This is cool. This is an ellipsoid. And it's centered at the origin, right? And this simply says, this thing here says that all the V's are in the ellipsoid, right? And so what this says is, here's how you find, this tells you that there's a relation between this experiment design and actually you take your V's, then find the minimum volume ellipsoid centered at the origin that covers them. And there's a close relation to that. In fact, there's weird complementary slackness would tell you this, that the one it touches when you find this minimum volume ellipsoid, it touches some of the points. Those are the experiments that are desirable. We'll look at some pictures of that in a minute. Here's one. Okay, so here's the origin, right? And then here are the experiments you've been offered. I don't know, maybe there's 20 of them, like 10 here and 10 here, right? And let's see, let me ask a couple of questions. Okay, clearly these are more desirable than these. How come? And just roughly. Why would these experiments be more powerful than these?
More SNR.
They're farther from the origin. That means VI is bigger. It means the signal noise ratio is higher, right? Okay. Now here. So this is the minimum volume ellipsoid. You take an ellipsoid, shrink it. We'll see how to do that very shortly. You shrink it until it just touches 2, and that's this one and this one. And it says that you should use the high SNR options. I mean, right, that's what it says. And why does it pick this one and that one? It's in 2 dimensions, right? How come? Yeah, that's right. You take the two high signal to noise measurements, which are closest to orthogonal, or they kind of give you different information, right? If you're saying this is the way you should aim your radar, it says, yeah, ideally I would love to have this shot and then 190 degrees like that, right? That hasn't been offered me here, right? Let me ask a question. What if I shrunk these down to just a little tiny arc? Someone guess. What do you think? Actually, when I put it somewhere else, I mean, not it shouldn't reflect this thing, right? But suppose I put these things like up way up, like over here, and I shrunk them down to just a few. What do you think would happen? At some point, you probably wouldn't take 2 because they don't have enough different of a view, right? And that means that they're not going to give you, so you'd end up picking one of these. You don't want to, but you'd pick it because you need this kind of diversity to be able to see what it is. Okay, everybody, all this makes sense? Okay, so this is the optimal experiment design. And it says you should make these both 0.5. I mean, who knows why? Because maybe it's symmetric. By the way, there's a ton of super fun things you can add to this, right? So here I just said, these are your measurements, right? I could attach to each measurement a cost. And I would say, I could give you a budget in cost, right? The cost could be, let's say, the energy you use to carry out that experiment, and you want to preserve your drone battery life. Everybody following this? And that's actually, how would I change the convex optimization problem to adjust? How would I change this for that? What would I do to include a budget there? Then you could have all sorts of interesting stuff. You could have really high signal noise measurements, but they cost a lot of joules. Okay, and I mean these are not made up. This is exactly how kind of things work. But any. Yeah.
Would that be a linear constraint?
Yeah, this is a linear. It's C transpose lambda is less than a budget. It's nothing more, right? You could do other weird stuff. Here's one just for fun. Let's suppose this is actually like a drone or so. Suppose it turns out that you get that it's free once you do one experiment of one type, you get a discount on like 2 others. Because once you fly to that place, you might as well turn on your LiDAR and blah, 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 and all these other things, right? Or something like that. And we could just talk briefly about that. How would you express that? Any, how would you do that? Okay, I'll put it this way. I'll leave it for you to think about. Those are convex constraints, and they start getting really sophisticated and quite interesting. Everybody understood what I just said? Yeah. So yeah, no. It's a weird thing where you say, well, if you use that sensor, you might as well also use this one. You get a discount. Could even be free, right? So okay, I'll just leave it this way for now. Yeah. Okay, I'll leave it. We'll move on to the next topic. Okay. So let me just end this by saying the idea of this experiment design stuff this is only for linear measurements with Gaussian noise, right? All other experiment design things get unbelievably complicated. They're basically sequential decision making under uncertainty and things like that, and they start getting really complicated. But for this one case, which is actually kind of interesting, it is weird if you think about it. There's a lot of weird things about Gaussians and things like that. But this basically says you can say ahead of time how well you're going to do. If someone says, "There's my flight plan," how well am I going to estimate this thing? You can actually say, right, ahead of time before doing it, right? Whereas for other things, you can't do that for the distribution. Anyway, I won't. I just want to warn people about that. Okay. I'm going to skip the derivation of the dual, and we'll go on to the next topic. Oh, question? Yeah.
Quick question.
Yeah.
For the dual problem, how do we get the minimum volume ellipsoid?
Oh, you mean how? Do you mean the interpretation of it?
I mean, it seems like a maximization. So.
Yeah. Well, so I have to ask you, what is the volume of this ellipsoid? That's going to be kind of our next topic. What's the volume of this ellipsoid? I mean, right. Okay. Let's go real slow. If W is big, like as a matrix, what can you say about the ellipsoid there? It's small, right? So in fact, the volume, I don't even remember what it is. It's the determinant of W, I think, to the -1/2, and then multiplied by the volume of a unit ball in R, whatever it is. In this case, maybe RP or something like that, right? Which has got some gamma function and some weird factorials and who knows, probably some pi's in there, I'm guessing. That doesn't matter, right? So the volume of this is a constant times the determinant of W to the -1/2. And that says if you make W, so minimizing determinant of W to the -1 over the square root of that is the same as maximizing the log determinant. So that's what that. So I didn't say that, so it's kind of unclear. But yeah.
I forgot about the big W means the small.
Right. That's for this parameterization of an ellipsoid, because we're about to see some others. Okay. So now we'll do geometric problems. Actually, I don't even have here, I'm going to mention some really simple ones. They're so simple that it's almost like insulting to ask, but let's just start with some really simple ones. Suppose I gave you two polyhedra, like P is the set of X for which, AX is less than B, right? And let's say P tilde is the set of X for which A tilde X is less than B tilde. So these are two polyhedra, right? And suppose, how would you solve the following problems, right? How would you determine if they intersect? Is it a convex problem, and what problem is it?
Is it like a feasibility problem that satisfies both constraints?
That's it. It's just a feasibility problem. So you'd say, yes, you can solve that. It's convex. It's an LP feasibility problem. Okay, I'll take it up one notch. Find me the minimum distance between the two polyhedra. Let me explain what that means. It means find me a point, in one, and a point in the other, for which the distance is as small as possible. What kind of problem is that?
Least squares with constraints.
Yeah, it's a QP, right? I would say it's going to be, I would have these constraints, ax less than b, and I would write ax tilde less than b tilde, and I would minimize simply x minus x tilde. There. Any norm you like, but we'll take 2 norm. Everybody got that? So these are just unbelievably simple problems now, right? Oh, and what if the two polyhedra intersect? And I ask you, find the distance between the 2 polyhedra. Yeah, it's a 0, and you name any point, and you go, wow, how could it be 0? And you go, well, because this one vector is in both polyhedra, and the distance between a vector and itself is 0. Everybody got this? Okay. So, I mean, these are simple things, right? So, we could go on and on. What if I represented, the polyhedra by a list of its vertices, right? Suppose I have P hat is the convex hull of V1 up to Vn. Ooh. Now, how do I determine if this intersects that? Any suggestions? No, it's a different representation, right? So, any suggestions? Is it a convex problem? How would you solve it? Yeah.
Use like weights as your variable?
Precisely, right? I would make one variable is going to be some theta I vi. The theta I are positive and they sum to 1, right? That's my variable theta, right? And if I want to do this, I would actually write this equals x, right? And then I would also have ax less than b. Everybody see this? And so what that is, and now I solve that feasibility problem, which is an LP feasibility problem, but really who cares, right? I solve that problem. If this is feasible, then this polyhedron described by its vertices intersects this one described by its inequality constraints, right? If this is not feasible, they don't intersect. Everything. So anyway, these are very basic ones. You can read about them in the book, but in a way, like at this point in the course, you know enough that these are just almost too simple to even, I mention them, right? But that's the idea. So we are going to get to ones where things are not obvious at all. And that's actually the first topic. These are kind of obvious, right? And you go on and on with different geometrical problems. And these things obviously come up all the time in things like, robotics, if you want to know, if you have a polyhedral, thing of, if a polyhedron represents a vehicle, and then you have a polyhedral safe space or something, and you want to know anyway, I won't, or an obstacle, right? And you want to know, what's my distance to the obstacle or something? Okay, so, all right. So now we're going to look at ones that are not obvious at all. And these are going to be, I think these are all pretty simple, right? This gets very weird and cool. And it's more than 100 years old. So here it is. Suppose I have just a set C in Rn, right? And what I want to find the minimum volume ellipsoid that covers it. Okay? So that's, that's got a name. It's called the Lohner-John ellipsoid of a set C. And now we're going to show you how to pose that as a convex optimization problem. And this is actually, it's interesting. Now you have to be very careful because there's lots of parameterization of ellipsoids. And for each of these problems, we're actually going to take different parameterizations because in that parameterization, it's going to be convex. And in another one, it will not be. So you have to be completely on your toes on these things, right? I mean, the truth is we already saw it. We didn't mention it here, but for example, if I ask you to estimate the covariance of a zero mean Gaussian vector from data, right? Then it turns out the log likelihood is not concave in sigma, the covariance matrix. It is concave in the inverse, which is the precision matrix. Okay, so if you know what I'm talking about, fine, and if you don't, that's fine too, right? So that's a case where there's lots of ways to say what a covariance matrix is, right? You could give its inverse, you could give it, and it's going to turn out some things are convex in one but not the other, and so on and so forth, right? And this is similar. So here we go. So we're going to do this. I'm going to write the ellipsoid, I'm going to parameterize it by a matrix A and a vector B. And it's the inverse image of the unit ball under an affine mapping. Okay? Everybody got that here? So that's what it's going to be. Okay. And here, I'm going to say that without loss of generality, I'm going to assume A is symmetric and positive definite. Okay? I mean, okay, so it has to be just positive semi-definite because I want it to be invertible here, right? Otherwise, that's not an ellipsoid. It's got like a whatever. It's got some infinite, it goes in, it's a cylinder, I think is what people call it, or something like that. Okay. So I would like to know if someone says, yeah, I have a parameterization of ellipsoid with an A and a B, but my A is not symmetric. So I need someone to help me to see why we would say without loss of generality, right? This is a subtlety, right? So, but an important one, right? So it's a set of X for which AX, I can't remember, is it plus or minus B? AX plus B, right? 2 norm is less than 1. Someone gives you this, but A is not symmetric. So, or it's not symmetric and positive definite. So A is invertible. So any suggestions on what we can do here? They give you a lower triangular matrix. I don't know what they give. They give you something like that. So what do I do? Any, yeah.
Singular value decomposition.
Yeah. Let's write U. Let's A is U sigma V transpose. Those are all square because it's non-singular. Okay? Does everyone agree that if I took this vector and I put in here an orthogonal matrix, then nothing has changed? I could put a Q in front here, which is orthogonal, and this constraint is identical, because if I rotate something and if I rotate the unit ball, you still have the unit ball. Everybody cool with that? Okay. Can someone suggest a Q I should apply to this? And I want to apply a Q, which is going to have no effect whatsoever on this, but it's going to render this thing, when I multiply by Q on the left, this thing is going to come out positive, definite, and symmetric. So I'm open to suggestions for what Q is.
VU transpose.
Yeah, there you go. Q equals VU transpose. That's orthogonal. These are both orthogonal. These are orthogonal. So if I plug that in there, then A is now going to be V sigma V transpose, which is symmetric and positive definite. Everybody got this? Okay. So it's a subtlety, but it's actually going to be super important. Okay. And then it says the following. With this parameterization, the volume is proportional to the determinant of A inverse. Right. And you can figure that out, right? If A gets big, then the ellipsoid gets small, right? You can kind of see that, right? And so the volume is proportional to det A inverse. And in fact, I think the proportionality constant is this magic number, which is the volume of a unit ball in Rn, which has some gamma functions and probably some pi's in it and other stuff. Doesn't matter. It's a constant, positive constant for us, right? So, okay. So this thing is going to, this is the same as minimizing the volume of E. Then the other thing we have is that we have to have that every element of C has to be in this ellipsoid. And the way to express that is this. It says that if you maximize over C, AV plus B, right? In 2 norm, if that's more than 1, then you're not in E. If it's less than or equal to 1, you're in E. Everybody got that? And now we have to stare at this, and you really have to concentrate. Let me give you a couple of the warnings about why you have to concentrate now. Because the variables in this problem are capital A and little b. I mean, the usual convention is that A, B, C, D are like data. They're constant, right? And the usual convention is the variables are things like u, v, x, y, z. Everybody following this? That's usually, right? But here, well, v is a dummy variable, so it means absolutely nothing, right? But here, so we have to ask, is this thing, and A is, of course, symmetric positive definite. This is convex, log determinant, A inverse. What kind of constraint is this over A? I mean, it's convex. Why? Because if I fix a v, what kind of function is that of A? If I fit for a fixed v, it's convex in A and B. Sorry, it's jointly in A and B. It's convex. Matter of fact, the argument here, AV plus B, is a linear function of the pair AB, right? Not even affine. It's just linear, right? And so this thing for a fixed v is a convex function of the pair AB. That's a supremum. Doesn't matter what C is. That the result, this left-hand side is a convex function here, right? So that's a convex function, and it's less than or equal to 1. Everybody? So this is a convex optimization problem. Okay, so this is how you would minimize the volume of an ellipsoid that covers a given set C. Now, we have to turn this into something reasonable. It's something that we can handle, and we'll do that. Here's a super simple example, a finite set, and you have m points, and you end up with a completely reasonable thing. It just looks like that, and that's a convex problem. You can solve it, and it just works, right? It gives you the minimum volume ellipsoid. So if I give you a bunch of points, by the way, that has a whole lot of applications. I'll just mention one for fun. Right, so here's a bunch of points like that, right? Right, and then oh God, I don't know what I'm going to do here. Okay, so then you get some ellipsoid that looks like that, right? And that's going to be the minimum volume ellipsoid that covers those points. Everybody following this? So here's actually an interesting way to suppose these are like, not in 2 dimensions, it's silly, but suppose it's in high dimensions, and I want to ask which of my data points here are like outliers. Just like that. I don't have a statistical model, although that would be a reasonable way. So what would be some reasonable ways to say something is an outlier?
It's close to the edge of the ellipsoid?
It's what?
It's close to the edge.
No, I haven't computed this yet, because let's just do like, how would you do it otherwise? Well, you could actually find the mean. Here's one. You could find the mean and the covariance of the data points, right? And then you'd look at the what so-called Mahalanobis, distance or something from the center, right? That would be a reasonable way. Or you could look and just say, well, which of your points are really big, right? Those are outliers, right? This is actually a quite good one, right? It's entirely dependent on the outliers, right? Because you can kind of see that if you shrink an ellipsoid down, it's going to stop when actually generically n plus 1 over 2. But if that's the dimension of points are on that ellipsoid, right? So there's a method for removing outliers called ellipsoidal peeling. It's awesome. First of all, it's a great name, and it's also a pretty good method. And it works like this. You say, thanks for the data. You find the minimum volume ellipsoid, and you find the points that it touches, right? Those are the ones for which this constraint here is equal to 1, okay? Then you declare those to be outliers, and you remove them, and you continue until you like what happens. Like, for example, you're out of sample, whatever. If you have some other test, you can check, your estimator gets better, or something like that. Everybody following this? Okay. That is very cool. Okay, let me ask one question just for fun. Suppose that you do that, and I have, hundreds and hundreds of points, but let's say that 25 have satisfied this with equality. Everybody following this? 25. And you'd say, I'm going to remove them. There's 25 outliers. And then someone says, please don't. You go, why? Because, look, there's no way we have 25 hours. We actually only have 5. I couldn't imagine it being more than 5. Everybody following this? Could someone please suggest how you might choose the candidates to remove? Sounds like a trick question. It's actually not, and it tells you if you can, it's easy if you can use the material we've looked at. I compute the minimum volume. Let's review. I have a whole bunch of vectors. I compute a minimum volume ellipsoid. 20, let's say 22 of the points are actually on that minimum volume ellipsoid, meaning that constraint is tight for 22, right? I say, take them all out. And they go, no, you're throwing away too much of my data.
You eliminate the ones that are on like the far edge of the.
Yeah, but what's the far edge of an ellipsoid? I don't think that works, right? Was there another suggestion?
Maximize the difference in the volume from the original to when you remove 5 of the points.
Yeah, these are pretty. That's something like that might happen. Was there another suggestion? Yeah.
Just randomly throw out.
Oh, okay, that would be fine. How about you say here, ellipsoidal peeling says that these 20 are bad, and they say, no, I can't imagine having more than 5 outliers. And you go, cool, and you just remove the first 5. That's your suggestion? Okay. No, I like it. That's a good street fighting thing. You don't say it like that to the person. You just go, oh, hang on a minute, and you go back and you pretend to change the code and stuff like that. Okay, and then you do that. Okay, that was another suggestion somewhere. All right, I'll try one more time. Yep. To see if I can elicit a response, okay? I have 20 constraints that are tight. I would like to remove 5. In fact, I'll even say I want to remove the 5 tightest constraints. How about that? Please? What? Oh, there we go. Okay, fine. You get the dual variables, which you get for free. And then you remove the 5 with the 5 largest dual variables. Everybody cool? That's it's pretty sophisticated. I mean, we're just putting ideas from the class together. This is not, but things like this are actually kind of useful. Actually, that was a good question because it's the ones we like, right? Because I didn't say the D word, which is duality. But that was a question about duality. So what we want is we want you to have a street fighting idea, knowledge of duality, because it never ever works when someone comes and says, oh, help me, I have a dual. And you're like, no, it doesn't work that. The way it always works is somebody has some long complicated problem and they need a suggestion. And they don't even know what duality is. Right? So, okay, everyone cool? That was just an aside, but it was fun for me anyway. So, okay. Okay, so this gives you the minimum volume ellipsoid. Okay, so then you could say, okay, fine. Can we do, let me just ask, I'm going to go back and show one of the, so you say, that's cool, you can do a minimum volume ellipsoid around a point, and then you might innocently ask, well, that's cool. By the way, this is the minimum volume ellipsoid that covers, a polyhedron given by its vertices. So that's the same problem, you agree? So if someone walks up to the street and says, find the minimum volume ellipsoid that covers a polyhedron described by its vertices, then that's also, we can do that. It's a simple convex problem. Cool? But now someone says, oh yeah, you know what though, my ellipsoid is described by not vertices, but it looks like this. Here's my ellipsoid. It's described by a set of linear inequalities. And we want to find the minimum volume ellipsoid that covers, that covers a polyhedron described by its faces, right? Everybody cool on this? Okay. It sounds reasonable. Actually, someone give a simple, I mean, what would be one way to do it? What would you do?
In the intersection of all the inequalities in them.
Yeah, so you would basically, you'd first write a method that called, faces to vertices, right? And you'd take your ellipsoid and you'd call the faces to vertices method on it, right? And it would give you the vertices, and then you type this in. It's 3 lines of CVX pi. That's your proposal, right? I like it. It would work. There's one minor problem with that. is how many vertices, just order magnitude, does a polyhedron in R1000 with, let's say, 5,000 inequalities, which, by the way, is a tiny thing you can solve on. You can solve an LP or problems with that on your phone. Everybody got that? How many vertices does that have? About, just order magnitude. Everybody know what I'm saying? I mean, I'm not drawing a picture here on R2. I'm talking about R1000 or whatever, and you've got 5,000 inequalities. How many vertices does it have? A lot. Yeah, that's the answer. It's order magnitude 1,000 choose, whatever, 5,000 choose 1,000. Just for the record, that's a super big number. So your method was correct. It would work in 2 dimensions and 3 and blah, blah, blah. It's not going to, it would be absolutely correct. It just wouldn't work for big. Okay, everybody got that? Okay, so now I'll let you in on the secret. It turns out, actually, finding the minimum volume ellipsoid that covers a polyhedron given an inequality form is NP hard. As a matter of fact, the following is, I just walk up to the street and say, here's an ellipsoid. Like, don't even optimize it. Here's an ellipsoid. And I ask you the following innocent question. Does my ellipsoid cover this polyhedron? Makes sense, right? So, I mean, you could even imagine all sorts of, things that people might use this for. They would say like, my polyhedron is my desired region or something like that, and I'm going to cover it with an ellipsoid. You just want to ask, does it cover it? Anyway, everyone got the question? Unbelievably simple to state. NP hard. Okay, so it gets these things are about to get very weird. Okay, so it depends on how you describe the polyhedron and all that kind of stuff. Okay, so yeah, if you're confused, you should be, right? Because this is quite complicated. Okay, now to confuse you, if you're not yet confused, this should do the trick. So now we go to something like a dual problem. It turns out they're not really duals, but that's okay. The dual problem is, I have my set C. Here, I'll just draw a C. Here's C, right? And what I want to do now, the Lohner-John ellipsoid covers, is find the minimum volume ellipsoid that covers this thing, right? Now, this is a variation on that. This doesn't have a person's name attached to it. Or I guess I should say, that's this one. It says, find me the maximum volume ellipsoid that fits inside your set. Okay? Here's what's going to happen. This is crazy. If the set is an ellipsoid, if the set is a polyhedron, we're going to be able to solve this one when these are given by inequalities. Totally straightforward. But if it's given by the vertices, it's going to be NP hard. So it's just weird and crazy. I can calculate the maximum volume ellipsoid that fits inside a polyhedron described by inequalities. That's easy, tractable. I can find the minimum volume ellipsoid that covers a polyhedron described by its vertices, totally tractable. Everybody following? But the 2 other problems are actually extremely difficult. Everybody got that? So it's interesting actually. Okay, so let's see how to do that. Now to do that, what we're actually going to use the opposite parameterization we did before. Before, to find the minimum volume ellipsoid, we used the inverse image of the unit ball under an affine mapping. Here, it's going to be the forward image of a unit ball. So here's the unit ball, and I'm going to make a forward image under an affine mapping, right? So here, by the way, the bigger B is, the bigger E is, right? Whereas the opposite was true for the previous parameterization. So we do this. And here, once again, we can assume without any loss of generality that B is both symmetric and positive definite. Okay? So B is invertible, but I can do that. And I do the same trick, right? Here, if I put a orthogonal matrix if I replace B with BQ, the problem is identical. Because Q multiplies U is in the unit ball. And if I have an orthogonal matrix there, it doesn't change anything at all. Everybody following this? Okay, so that's my parameterization. And now the volume is proportional to the determinant of B. So if we maximize log determinant B, that's the same as maximizing determinant B. And that's actually log determinant B is, as you know, concave. And then we're maximizing so everything is cool. Everybody Following this? So, okay. Now we have to be able to say that the following is true. I want to say that everything in this ellipsoid is inside my set, right? Because that my ellipsoid has to fit inside the set. And the way you test that is this: I'll take the indicator function for C, right? And that's just something that's 0 if you're in C and infinity otherwise. And I write it this way. So I see a BU plus D means, let's see, what does it mean? It means if this element is in C, this is plus infinity, otherwise this is 0. Okay? And this is silly to say sup, U less than, it just says that basically for all, it says basically everything of the form BU plus D with norm 2 less than 1 is in the set. That's just a fancy way to write it. Okay. Now this is actually, this is a convex optimization problem, but once again we have this kind of a weird supremum or infimum in the problem, which we know it's a convex, but we have no way to write it down. It's not tractable. And so actually this is the point in the course when we can start, basically level 0 is convex optimization problems are tractable. That's like if someone on the street asks you or whatever, like, hey, or from a different field asks you, who cares about that? And you go, well, they're tractable, right? But now you can see that's actually false because this is an example of a problem where, you just have some tractable. Actually, the ones I said were NP hard before, they're convex problems. No problem. They just have this, they just have this infimum or supremum in there that you can't represent, right? So, yeah, so it depends. You have to judge the social, it depends on the social setting, right? If you're with a bunch of mathematicians or people who know a lot, then you don't have to, you wouldn't say all convex problems are tractable, right? So, okay, all right. So here, let's do a polyhedron, and then I can check, right? So with this parameterization, if I want to know is E inside this polyhedron given by a set of inequalities, that's actually completely tractable, and it looks like this, right? That's a perfectly good problem right here. Maximize the log determinant subject to, and let's be very careful. You have to be really on your toes here. What are the variables in this problem? What are the variables? Capital B and little d. Is that right? Yeah, okay. And then what are AI and BI? What are they? They're data or constants or parameters, however you want to say it, right? Okay, so then what kind of function is this of the variables? It's convex. It's BAI is linear, and then it's a 2 norm, so that's convex, right? What kind of function of the variables is that? Yeah, it's affine, but it's linear, right? So, it is affine, of course, but it's even linear, right? And so this is a convex constraint because that's a convex function, right? In fact, it's second order cone representable, right? So, okay, so that's it. So this is this crazy thing where if I give a polyhedron, if I give you a polyhedron described by inequalities, we can find the maximum volume ellipsoid inside it. Everybody got that? And that's completely tractable. By the way, this has tons of applications immediately. Like, suppose I give you a polyhedron that's very complicated, defined by inequalities, and you say, that's a safe operating region, right? If you're state or whatever it is, if you're a robot, whatever, if you're in that, you're not going to hit anything and it's safe. Everybody following this? This allows you to do something like make a guaranteed, the maximum volume safe ellipsoid. And someone say, why would you do that? You say, because my algorithm that manipulates it can handle an ellipsoid, but not a polyhedron with 80 faces or something like that. Everybody following this? So this already has a lot of uses, right? That's one, just right there. Okay. Now it turns out there's something very weird about these. Actually, it's very cool. It's this. This is math, right? But it's actually super interesting and has all sorts of implications. So here it is. Take any convex bounded set with non-empty interior, right? So it's not flat. it doesn't go off to infinity and blah, blah, blah. There's C, right? Then the Lohner-John, by the way, we're not talking about whether or not you can compute the minimum volume ellipsoid that covers something or the maximum volume ellipsoid inside it. That's a separate question. This is math, so we're unbothered by the questions of, we're just looking at what's true and false, not how do you actually, how much trouble is it to compute it, right? So, okay, so it turns out that if you take the Lohner-John ellipsoid, so that says take your set, you find the minimum volume ellipsoid that covers your set. Then it says shrink the set shrink that ellipsoid around its center by a factor n. Everybody got that? That's inside the set. Okay? That's what it says. Okay? And the opposite is true for the maximum volume ellipsoid. If I have any set at all, convex, I find the maximum volume ellipsoid that fits inside it. Now, I expand it by a factor n about the center. That covers the set. Okay? And it gets even weirder. If the set is symmetric, like if minus the set is equal to itself or something like that, then it turns out you don't have to have a factor of n, you have a factor of square root n. Everybody following this? Now this actually tells you unbelievable things. This says that if you had a convex set and you approximate it with an ellipsoid, it says you can't be too far off. In fact, if I take, let's say, either the Lohner-John or let's suppose I take the Lohner-John ellipsoid and I shrink it by, suppose I shrink it by square root n, right? And I say that's the ellipsoidal approximation of my set. And you go, cool. How does it approximate your set? You go, well, if I expand it by factor square root n, it covers my set. If I shrink it by a factor of square root n, it's inside the set. Everybody got it? So actually it's kind of, what it tells you is that like ellipsoids are universal approximators of convex sets. Right? Now square root n in some practice might be like way too much for you to be happy with or something like that. But actually let me do an example here. Let's just do one here. Here's my set, ready? It's a triangle like that. Okay? What's the Lohner-John ellipsoid of that? It's a, equilateral or whatever they call it. What's the Lohner-John ellipsoid? It's just a circle that goes around it, okay? Right, so it looks like this, right? This is gonna be terrible, but okay, there it is. Okay, right? Okay, shrink that by a factor of 2 in your eye, and what do you get? You get this, right? And actually this example shows that's tight, that inequality, right? So, and in fact, it's always true. So you could even say something very weird like this. First you say, all convex sets can be approximated by ellipsoids within a factor. You could say, I could say square root n because I'd put it in the middle and then both expand and shrink, right? And you'd say, yeah, well, what are the hardest sets to approximate by ellipsoids? Makes perfect sense, right? And the answer is a simplex in Rn. A simplex in Rn, if you want to approximate it by ellipsoids, it's going to take the full, square root n. Here would be my weird square root n thing, right? It would be something that looks like that. Whoops, okay, that came out very poorly. But anyway, this would be my square root n. And I would say, you see that ball, that disk? If I increase it by 1.4, whatever, 1.42, there you go. Then I cover my triangle. And if I shrink it, if I multiply it by 0.7, then I'm inside. Everybody got that? And then so everybody got all this? So this applies actually weirdly to norms, right? It says take any norm at all on Rn, right? Any norm. It says that I can replace it with a quadratic, I can approximate it with a quadratic norm. Those are symmetric. With error no more than the 4th root of n. Okay? So now I'll tell you an important thing about that. There's lots of norms. Like here's a norm. The minimum fuel it takes you to go from a state to 0. That's a norm. That's actually a norm. It's a crazy polyhedral norm, right? With lots of it's a crazy norm, but it is a norm. But that might be one we really care about, right? It says I can approximate that like pretty well with a quadratic norm. Why does that matter? Because in fact, the control that people actually use is all based on quadratic stuff. And so this would give you a very good way to find those to find the actually it would actually say kind of why things work so well, right? When people would say like, yeah, how are you controlling your airplane? And if they're honest, they'll say something like, well, it's basically using something like linear quadratic. Basically, it's almost least squares. Basically, it's more complicated than that, but not too far. And you go, whoa, you go, that's great. Are the are your actual constraints like spherical or whatever? And they're like, no, they're not. That kind of thing. So, but it works really well, and this is actually, at least I like to think, part of the explanation. Okay, so does all this make sense? It's kind of weird and interesting and cool, I think. Okay, next topic is something we've actually seen a couple of times before. It's so-called, it's centering. So actually, very early in the course, we encountered this. It was one of our first examples of a linear program, right? It was like, here's a polyhedron given by inequalities, and I said, find the largest ball, Euclidean ball, that fits inside it. Everybody got that? That's called the Chebyshev center. And it's an LP, and I said at the time it's weird because if I say things like Euclidean ball or draw a circle, the linear programming part of your brain should not be lighting up, because that's linear programming part of your brain should light up when I say things like polyhedron, inequalities. Visually, you should be seeing flat things with corners, right? You should see like a modern, fighter jet with, made with like flat parts and stuff like that for various reasons, right? That's what you should be seeing. You should not be seeing beautiful curves. I mean, anyway, that's what you should be seeing, right? And so that was weird, but that's it. Okay, so that's the Chebyshev center. But we have another one immediately. Oh, we saw another one. We saw the yield center or probability center. So that would be, take a point, and then you're shifting the mean. Now put a zero mean distribution around it, and with a log concave density, and then pick the center that maximizes the probability. That's another one. I think people call that, different fields, they call it different things. It's like the yield center, or I don't know. There's all sorts of names for it. Or probabilistic center. But here's another one, the center of the maximum volume ellipsoid, right? And that's actually a very good one for reasons I'll get to, but not today. Okay, so this is centering. It turns out, of course, look, centering. Let's talk about centering in R. It's going to be a very short conversation, right? So here's a convex set in R. It's called an interval. What's the center of an interval? A bounded interval. What's the center of the interval? It's the center. It's the middle of it. I mean, come on, that's what it is. And there's no other reason. You say, no, I think it should be the one that's 1/3 of the way towards the left. And you're like, what does that mean, right? So but the minute you get to like R2, it's actually interesting. It turns out there's multiple different definitions of a center, and we're going to look at some of them. So just to point this out, right? Okay. One thing that's going to come up later is the so-called analytic center, and it's actually a weird thing. It's a bit. I'll say why it's weird in a minute, but it's actually not. It's not a center of the geometrical object. It's actually of a set of inequalities. So if I have a set of inequalities and some equality constraint, if I maximize the sum of the logs, these are the margins. Fi should be less than 0, so minus Fi should be positive, right? Or non-negative, right? But here, this says basically maximize the product of the margins. That's called the analytic center of these inequalities, right? And it's going to turn out that's very easily computed. As a matter of fact, you will be computing it in about 2 weeks. So you'll be writing code to do that. Anyway, so I think what we'll do is we'll quit here for today, and we'll continue next time.